Okay, so let's get started. So let's start with where we left in the last class. So in the last class, first we started with a two-step converter, right? So I think that part was completely clear. Okay, and then we saw how we can extend this two-step conversion to a three-step conversion, right? And the basic idea here is to assume that you have, it's not highlighting. Okay, yeah, the first ADC here, and instead of using a normal ADC here, the second state itself is a two-step ADC. Okay, and if you assume that this two-step ADC here produces an output, say V2 hat, right? So now we can combine the output of these two ADCs as the first output V1 plus the second output V2 hat by the gain you are adding here. That's fine, right? And now if you consider this part alone as another two-step ADC, so how do you get this output? You have these two, V2 and V3. The output will be the first stage output, that is V2, plus the second stage output, that is V3, divided by the gain you have here, G2, right? So if you plug in the expression for V2 hat in here, what you get is V1, that is the first stage output, plus V2, that's the second stage output, divided by the gain it sees before, that is G1, right? Plus the last or the third stage output, V3, divided by the gain it sees before, right? That is G2 times G1. That's all. Okay. And if you find individual expressions for V1, V2, V3, what you get? V1 is simply the input here plus the quantization noise, U plus Q1. What is V2? V2 is simply the input here. And the input here is what? It is minus G1 times the quantization noise you add here. Okay. So this is minus G1 plus the quantization noise you add here. So that is this minus G1 Q1 plus Q2. Okay. So what is the input here? This is minus G1 Q1. This is minus G1 Q1 plus Q2. So that gives this to be minus Q2. So the input to the third ADC here is minus G2 Q2 plus the quantization noise. That gives V3. Okay. So now if you plug in individual expressions for V1, V2, V3 here, you find that finally you have only the input plus the quantization noise of the last ADC Q3 divided by the overall gain G1, G2, right? So the point to notice, the quantization noise that is added by all the previous stages, that is the first stages here, they are getting completely cancelled, and you are only left with the quantization noise of the last stage, and that is in turn getting divided by all the gains it sees before. Okay. So now if Q3 is coming from an ADC which has a resolution of B3 bits, and we saw that G1 we choose it as 2 power B1 and G2 we choose as 2 power B2. So we saw the overall resolution of this portion is simply B1 plus B2 plus B3. Okay, this is fine. And as we also saw, the way to combine these outputs turns out to be pretty straightforward. All you need to do is simply concatenate the individual ADC outputs. That's all. So V1 will be the MSB bits, V2 will be the next MSB, and V3 will be the last LSB bits. That's all. Okay. You don't need an adder, isn't it? You just need to concatenate, right? So you have 2 bits. I have 3 bits coming from the second ADC, let us say. I'll just wire it in such a way that these 2 are the MSB bits, these 3 are the LSB bits, and send it to the output. That's all. Okay. So this is my MSB. This is MSB minus 1 and so on. The point is there is no need for an adder in this case, right? That's all. Is that clear? So yeah, and by the same token, we can extend this technique for n stages, and from this it's clear, right? So how do you get for n stages? So the way to recombine is we take the first stage output as it is. Second stage output will be divided by the gain it sees before. Third stage output will be the gain it sees before, that is G1, G2. Now you have one more stage, it will be here V4 by what? sorry, G1, G2, G3. Okay. Similarly, the last stage will be the last stage output divided by the previous gains it sees completely. Okay. And from the same expression you saw here, how do you think will be the output look like for the end stage ADC? Yeah. So can you say? I mean, I have. Let me write it here. So I have n stages, right? I combine in this fashion as we saw V1 plus V2 by G1 plus V3 by G1 G2 plus the last stage output by all the n minus 1 gains it sees before, right? So this will be equal to the input plus what? Q quantization noise of which stage? Last stage, is that clear? So last stage by, okay, that's all. So G1, G2 till Gn minus 1. And let us say G1 is 2 power B1, and let's say in general Gk is some 2 power Bk. What will be the overall resolution you can achieve with this? B1 plus B2 plus Bn. That's fine. Okay. So this is how you can get, you can realize an n-step ADC. Okay. So now let's kind of generalize it. So let's say I have a quantization noise Q that corresponds to an ADC which has a resolution of B0 bits. And let us say I'm dividing it by some gain G. So what will be the effective resolution of this fellow? I don't know what G is. Log in which base? Fine, is that fine? It's all right. So this is essentially B0 plus log to the base 2 G. Okay. I mean, this is simply assume 2 power some Bx and you find what Bx is. That's all. So I told, let's say you have quantization of Q that is coming from an ADC with B0 bits. Let's say that's getting divided by a gain G. I'm saying what will be the effective resolution of, that's all. Okay. If this was 2 power B1, this will be B1 plus B0, right? But in general, for a gain G, that's going to be log to the base 2G. Okay. So by the same token, here for the n-step ADC, can you say what is the effective resolution? Let's say Q1 is coming from an ADC with a resolution of Bn bits, and I don't know what these individual gains are. So what is the overall resolution? Sorry? This entire gain. Okay, that's all. G1, G2 till. Fine. Okay, so are you fine with this part? Let's say you have quantization noise that arises from an ADC which has a resolution of B0 bits, right? So if I divide it by 2, what is the effective resolution? I mean, the quantization noise is getting reduced by a factor of 2. No, for 2, yeah, log to the base 2 is 1, so it's simply B0 plus 1, right? So in general, for the gain G, it's simply log to the base 2G, that's all. Right? The same thing, I've extended it here, that's all, right? So now let's look at the timing or how the ADCs will work in real time. So let's say I take a 3-step ADC. Okay. And let's say these are the time points, TS2, TS3, TS, and so on. Right. And we have 3 ADCs, ADC1, ADC2, ADC3. Okay. First, you power on the ADC, only the first ADC will receive the input, right? That's input 1. These 2 ADCs will be idle. Okay. And when will the second ADC get the input? From this figure, you can see that the second ADC processes the quantization noise of the first ADC, right? So only after the first ADC processes the input, we can get the estimate of the quantization noise. Okay. So here, the second ADC can only process this input here only in the second clock cycle. Is that clear? Okay. So this will process here, and we can keep the first ADC idle. Third ADC has not received any input as of now. Now, in the third clock cycle, again, the first ADC can be idle. Second ADC would have finished processing the quantization noise. That's anyway the estimate of the input. And this gets passed on to the third ADC. Is that fine? Again, we can keep the second ADC idle here. Okay. So only after all the three ADCs have processed the input, you'll get the overall output, right? Because our output is simply this, right? V1 plus V2 by G1 plus V3 by G1, G2. Okay. So V1 you can get at this instant. V2 will get only here, and V3 can be obtained only here. Okay. So only at this time instant, you will get the first output. And if you continue this, what you can do at this point, first output is done. So now the first ADC can take in the second input, and this sort of repeats. So the second output will essentially come only at 60s, right? So this is how generic n-step ADC works. Okay. Exactly, that's what I'm getting at. Yeah. So this usually how n-step ADC as such in principle works. But obviously, you see this is not very efficient, right? Because the first ADC is kept idle here, right? Although input can still be given to it. So what do you think can be done? Yeah, that's exactly where I'm getting it. Okay. So if you have taken some course on computer architecture, you know how to parallelize operations. So the idea is, let me erase this portion. So the first, when you power on the ADC, these two ADCs will not have any inputs. That cannot be, I mean, we can't help with that. But after the first clock cycle, the first ADC has finished processing, right? Now, instead of keeping the first ADC idle, you can give the second input to it, right? Okay. So similarly, in the third clock cycle, the second input can be given to the second ADC, right? Instead of keeping it idle here. Okay. So second input can be given here. And in the third clock cycle, the first ADC can take the third input. Is that fine? So now at 3 TS, we get the first output. Right? I'll do the same thing. So in 3 will come here. 2 will come here. Okay. So the second output I can get at the next clock cycle itself. Is that clear? So this way you see that at each TS, you are able to make a decision on the input. Okay. So this way you're not compromising the overall speed, right? So if you had to do this kind of a process, you see that the output is coming at every 3 TS, right? So the sampling rate or the speed of the ADC has reduced by a factor of 3. Okay. But here, obviously, you see that for every clock cycle, we are able to get an estimate of the input, right? So this way you can take an ADC and or take multiple ADCs, each running at the same rate as this, right? Without compromising the speed, we can improve the resolution. Okay. And this obviously, as you know, has a name called pipelining. And this kind of an ADC is called pipelined ADC. Okay. So there are a couple of minor things to note. Now, although the output can be obtained at every clock cycle, so if I give the input here, when do I get the first output? After 3 TS, isn't it? If you just add one ADC, you would have got after one clock cycle itself. But now we have an additional 2 clock cycles of delay, right? So you have additional latency of 2 cycles here. Okay. And most of the cases, it might be fine, but in some cases, this additional delay might not be tolerated, might not be tolerable. And can you think of an example or a place where delay cannot be tolerated? Some kind of a system where you can't tolerate any additional delays. Okay, real-time systems is fine. Let's say I can have a delay. So someone told, yeah, negative feedback systems, right? If you have a negative feedback system, you know, if you have more and more delay, it will compromise the stability, right? So it is possible that this you might want to use an ADC in a big negative feedback system because you want to get an estimate of something and do some kind of a correction. Okay. So in these cases, this latency might not be tolerable, but otherwise, in many cases, this might still be okay. Right? And one more point. So write it here. So let's say you look at the output at this time, 3 TS. The output of the first ADC corresponds to third input, right? Okay. V2 corresponds to second input, and V3 corresponds to the first input. That's fine. So now, if I were to do simply V1, no, what I meant is the estimate of the first input is provided by the third ADC at this point. But at this time, the second ADC output corresponds to second input. First ADC corresponds to the third input sample, right? Okay. So if you were to recombine these three outputs as usual, that is, you take the output V to be V1 plus V2 by G1 plus V3 by G1 G2. Will this work directly? No, right? So what do you have to do? Sorry? Yeah, you have to store and delay it. Okay, because V1 is advanced version of it. In the sense, V1 is giving the third input, V2 is giving second, V3 is giving the first input. Okay, so you have to delay this by 2 clock cycles by giving it to 2 flip-flops. Yeah, 2 TS. So V2 will be delayed by 1 clock cycle, and V3 can be given directly. Only after you do this, you should do this recombination. Okay. So this all looks very good, but obviously there will be problems, and only if there are problems, we have some job and we have work to do.
So I just want to ask you about that. Like in computer architecture, there are some limitations of pipeline. If there is a miss, then we have to flush the whole pipeline architecture. But content of the whole pipeline architecture. But here I think this one should be not.
I'm not aware of this flushing business, but here you don't need, because you just what you need here is you have to sample the input, do the conversion. That's all, right? If you make a mistake on the first input,
That means that if I have an end state ADC,
right?
then I can use end level piping.
Yeah, this is. I mean, if you have n stages of ADC, it means you have an n level pipeline. That's all. I mean, just a terminology, right? And I mean, okay, this having 3 stages and operating all 3 stages concurrently is called a 3-stage pipeline ADC. That's all. Okay, this terminology. Yeah, and as I mentioned, this has its own problems, and you essentially have only 3 blocks here, right? One ADC, this multiplication or the gain, and the DAC. So let's see what problems can happen in each of these, okay, and see how they can be solved. First, let's look at the issues with the ADC. That is, what can go wrong in the ADC and what it results in a pipeline ADC. So for example, let's take a case where I have a 2-bit ADC as the first stage, right? And let's say it's getting subtracted. I'll not show the DAC for now for simplicity. Okay, here assume that there's a DAC here. I'm not showing it explicitly. So this has to be amplified. What is the gain of this amplifier? This is a 2-bit ADC, remember? 4, right? I'll write as 2/2. And this is given to the second stage. So let's say this is V1, V2. And for example, let's say this is a 3-bit ADC. Okay. So ideally, if I look at the quantizer characteristics of this 2-bit ADC, how will it look like? So let me quickly draw it. So let's say this is the input, this is the output. So say this is plus Vref and minus Vref, and this is say minus Vref by 2. Okay, so 2-bit quantizer has 4 levels, so we'll have something like this. Okay, this doesn't look very symmetric, but yeah. So this is Vref by 2. Okay. And of course, this is the straight line approximation. It doesn't look very great, but let me try to get it right. Okay, this is the straight line, which is input equal to output, right? So what is this level? Sorry, I mean, okay, sorry. This 0.25 Vref, clear, right? This is Vref by 2, right? So this has to be Vref by 4, and that's same as this, right? So this is, I'll just write VR by 4. Similarly, this is minus VR by 4. Okay, so let me take it to next page. So now if I look at the quantization noise and plot it versus the input. Okay, and let's say I plot minus Q1, that is I take the difference between the straight line and the step curve. Okay, this is essentially U. I'm taking the difference with this curve, which is U plus the quantization noise, that gives me minus Q, right? And this is versus the input. How will it look like? I'm essentially taking the difference between this straight line. Okay, this should pass through origin. Okay, my drawing is not so great, right? This is origin. Okay. So I'm essentially taking the difference between this straight line and this step curve. Okay. So obviously at this point we have a jump, right? So even the difference will show some sudden transition. And what will be the level of the transition? Vref by 4, right? Because see, at this point, the input is 0, right? But the quantizer, I mean, or this curve jumps from plus Vref by 4 to minus Vref by 4. So the difference will also jump accordingly. So this I'll just write as 1/4 and minus 1/4 for simplicity. Okay. And then you have, at this point, both this curve and this curve meet, right? I mean, at this point, there is no error, right? So this error should be 0. So it will do something like this. And again, at this point, which is Vref by 2, will show one more jump and do. Okay. Correct, correct. So what is delta here? No, I mean, it's minus Vref to plus Vref, right? Okay, delta is, yeah, correct, sorry, 2 Vref by 4, right? So delta by 2 is Vref by 4, and that's what happens here, right? It varies between plus and minus delta by 2. Okay, this is obviously the ideal case. So as we saw, I mean, as we have seen about ADCs, there will be a lot of non-idealities, right? And if we have a non-ideal ADC, how will the characteristic look like? The step curve. I mean, this is the ideal characteristic, right? Now, if we have some non-ideality, what will happen? You'll have everything. Okay, gain error, offset error, DNL angle. But the final reflection of all of these errors will be that these transition voltages will no longer be equal to these ideal values, right? That's all. That's a underlying thing, right? So now let us say, for example, this transition voltage shifts to this value. Okay. So now how will the quantization noise look like? Sorry. Again, if you point is, I'm taking the difference between this straight line and this characteristics. Okay. So now the transition, instead of occurring here, the jump is going to occur at this point, isn't it? So what will happen? This will keep growing like this, right? And at this point, it will make the jump. Is that fine? Okay. And the point to notice that this quantization error can exceed Vref by 4. Okay. Right? It's okay. I mean, simple thing is, you see, right? I mean, at this point, let's say at this point, somewhere in between, the output is minus Vref by 4. but the input is some positive value, right? So if you take the difference, you have some positive value, minus of minus VRF by 4, it's obviously greater, right? That's all. So now this is greater than VRF by 4, right? So in general, I can say mod Q will be greater than VRF by 4, right? Because if I have a curve that is shifted like this in the negative side, it will exceed. That's all. Okay. And for this 2-bit ADC, we saw the gain to be 2 power 2, right? That's what we wanted to use. So now if I use a gain of 2 power 2, that is 4, I'll write it here. What will happen to G times Q? Sorry? That's going to exceed VREF, right? So now this is going to overload the second ADC, right? And we don't want to do that. So what do you think is the solution for this? What can be done to avoid this? I mean, of course, one solution is to go back and sit and design the ADC to make the transition voltages very ideal. But obviously, you can't make it exactly ideal, right? So you can't do that part. So assume that there's going to be some non-ideality in this transition voltages. So in that case, what can you do so that this voltage doesn't exceed? Reduce again. So ideal gain is 4. So what do you want me to use the gain to be? Okay, I mean, take some simple guess, right? I'll take some 3. Okay, fine. So this is fine. This will definitely work. So let's see what happens now. So now the gain I'm going to use is 3. Okay. So how will I combine the outputs now? I have V1 and V2. How will I combine the outputs? 3. Okay. So now let's say V1 is 2 bits. So I'll have say some X1, X2, right? V2 is some 3-bit output. So it will be some Y1, Y2, Y3. And again, remember that I'm aligning MSPs. That's all you have to do. So these are all zeros here. Okay. So now how will V2 by 3 look like? It's straightforward. All right. But if you had division like V2 by 2 or V2 by 4, it's very trivial. Just need to right shift. Okay. So although in principle, this is a fairly good solution, this kind of complicates our computation. Okay.
So what we did?
Sorry? No, this is what you want to do, right? You want to combine the 2 ADC outputs in this fashion. Okay. I'm saying this is V2, some 3-bit output. Now, V2 by 3 is not trivial to write from this, right? We have to do computation, right? Multiplication with powers of 2 is trivial, just left and right shifts, but any other number is going to be involving. That's all. So what do you think will be a good value for a gain in general? Power of 2. Okay. So we generally want it to be some power of 2. Okay. And we also saw that the gain here cannot be exactly 2 power 2, right? So it has to be less than 2 power 2. So what is the thing? Right? In general, if you have a B1 bit ADC, I cannot have gain to be 2 power B1. So I use B1 minus 1. Okay. So now let us say I use this gain to be 2 power 1 here. So this gain is going to be 2. Fine. Again, I'll combine the outputs as V1 plus V2 by 2. Okay. So now V2 corresponds to, or sorry, if I write in terms of the input plus quantization noise, what will this be? Q plus Q1? No. Last stage, right? Assume that this is producing Q1 and this is producing Q2. Q2 by 2. Okay. So Q2 corresponds to 3 bits. So what does Q2 by 2 represent? 4 bits, right? So we have 3 plus 1 bit. Okay. So the overall resolution of this ADC is now 4 bits. Okay. So in principle, you could have got 5 bits, right, by taking 2 and 3 bits, but you are having one extra bit. That is, although output can have 5 bits, you are using it to represent only 4 bits of information, and that extra 1 bit is an additional or a redundant bit, and that is needed to tackle this kind of mismatches in the threshold voltages or the comparator transition voltages. Okay. Oh, sorry, it didn't go. Yeah, I told the extra bit we have is a redundant bit. Redundant, it's just additional bit, and that is just used to tackle mismatches in this or variations in the transition voltages of the comparator. That's all. Okay, if in principle you had this curve, you could have used the gain of 2 power b1, or in this case it's 2 power 2, and you could have got an effective resolution of 5 bits, right? True. Yeah, but yeah, okay, let's discuss it. He has a point. I'll come to that now. Okay. So let's try to see how the outputs will look like again. So V1 is a 2-bit output. So it's some X1, X2. V2 is some 3-bit output. So it's some Y1, Y2, Y3. So what is V2 by 2? How will V2 by 2 look like? So it's going to be 0, Y1, Y2, Y3. Okay. So now when you're combining the outputs, you're having this 1 bit of overlap. Okay. Fine. And obviously you can see that this sum can give a 5-bit output, right? Because if let's say the outputs were like this, say 1, 1, 1, 1, when you add it, this all zeros, right? So this will produce a carry, and this will produce a carry, and you can get 1 here. Okay, and this will be some Y2, Y3. Okay, so in principle, this sum will give a 5-bit output, but as we saw, the effective resolution is only 4 bits. So what does this mean? Sorry, we lose 1 bit. Yeah, 4 bit of information. So what it means is that even though you have 5 bits, at the output you will have only 16 possible codes. That's all. Yeah. Now it's no longer trivial. You can just simply concatenate. You have to add with 1 bit of overlap. Okay. And since we have this 1 bit of redundancy, although the output has 5 bits, if you look at the output codes, it will have only 16 unique codes. That is 2 power 4 codes. That's all. Okay. And this is again done to accommodate for the errors in these voltages, right? And you can find what are the 16 output codes you can get. Okay. So, and as he mentioned, if in principle, let us say this, there is no error here, the output here would have been from Vref by 4 to minus Vref by 4, right? And if you use a gain of 2, the output will span minus Vref by 2 to plus Vref by 2, right? So this is now going to be the input to the next ADC. Is that fine? So for the second ADC, it will again try to compare the input in this range, right? Minus Vref to plus Vref. But by choosing a gain of 2, we are restricting the input to the ADC in this range only. Okay. So the input will span only this, let's say this is 0, this is plus Vref by 2 and minus Vref by 2. So the input is going to lie only in this range. Okay. So you will not get any output codes corresponding to these ranges. Okay. So that's the answer to your question. Okay. I mean, that's what you are losing these output codes. And that is in turn reflective of the fact that even though you have 5 bits, you don't have all 32 output codes, right? 5 bits can represent 32 output codes. But since you are losing these, right, you'll only have 16 possible output codes. Okay. Is that fine? And this technique is usually called or referred to as adding redundancy, right? Here the redundancy in this extra 1 bit we are adding. Okay. The point is, although you want to realize only a 4-bit ADC, you are having one extra bit to account for any kind of non-idealities in the comparator transition voltages. Okay, so let's generalize it now. So let's say I have a 4-bit ADC here. Okay, and if I have 4-bit ADC, what should be the gain here? If I have a 1-bit redundancy, 2 power 3. Okay, fine, no confusions, right? So let's say this is given to one more 4-bit ADC. Again, if I have to have an amplifier here, what will be the gain? 2 power 3. Just need to look at this portion, right? This is a 4-bit. You need to have a 1-bit redundancy. You need to have a gain of 2 power 4 minus 1, that's 2 power 3. Right? And let's say this last, you have one more 4-bit ADC, right? And you recombine the outputs in an appropriate fashion. What will be the overall resolution of this ADC? Sorry, 10 bits. Is that fine? So this 4 comes from here, plus 3, plus 3. Okay. So this realizes a 10-bit ADC, right? But although in principle you could have had 12 bits, you are losing 1 bit each in these ADCs because of the redundancy. Okay. So now let's begin some. Let's look into each state. So looking here, this is a 4-bit ADC, right? That is this portion alone. Is that fine? So now if I have to look into this portion, that is, I look at this section alone, what is the effective resolution? Sorry, 7 bits. Okay. And of course, looking in overall here, it's going to be 10 bits. Okay. And again, one terminology. Right. Correct. Correct. You can do that.
So
yeah.
Better if I use.
Yeah, we'll see the choices, right? Now he's saying that the same 10-bit can be realized in multiple ways, right? I can have 3 4-bit ADCs, or I can just have a 4-bit ADC and a 7-bit ADC here, right? Sorry. Okay. The thing is, what he is asking is, this is not the only way to realize a 10-bit ADC, right? Here I'm having 3 stages, and here the overall resolution I want is 10 bits, but I can have 12 bits, right? I'm losing out 2 bits, right? You can think of it like that, right? 4, 4, 4, 12 bits I'll get at the output, but it has an effective information corresponding to only 10 bits, right? But he's saying, okay, why not realize the 10-bit ADC using a 7-bit ADC upfront and have a gain of 2 power 6 and a 4-bit backend ADC. So this also gives a resolution of 10 bits, fine, because this is 4 bits and the gain here is 2 power 6, 10 bits, right? We'll see in the later class. This is again a design choice, right? If you want to realize a 10-bit ADC, you can obviously have multiple ways to realize it. So going on later, we'll see the pros and cons in each choice. Okay. So now let's extend this technique, and let's say I want to realize, say, 10-bit ADC, or let's say I want to realize a high resolution ADC using a single bit quantizer, that is a 1-bit ADC, right? Okay, so if I have a 1-bit ADC, so I'll just say it's -1 and 1. I'm scaling the axis with respect to VREF. Okay. 1 means VREF, it's -1 means minus VREF, right? So if I have a single bit quantizer or a 1-bit ADC, the characteristics will look like this. Okay. This will be half, this will be minus half, right? And what will be the range of the quantization noise for a 1-bit ADC? For a 1-bit ADC, if I look at the quantization noise, what will be the range of voltages it will take? Minus 1/2 to plus 1/2, or minus Vref by 2 to plus Vref by 2, fine. And again, in principle, if you use a gain of 2, the gain times the quantization noise will span minus Vref to plus Vref, okay? But as we have just discussed, if we have, or first let me draw the quantization noise also. So the quantization noise is going to look something like this, right? Sorry. Or let me draw the straight line also. This is the input versus output. So it will look like this, right? Fine. This half and minus half. But as we just saw, if there is an error in this transition point, this will easily exceed half, right? And you will overload the quantizer. So what would be the gain you choose now? 1, right? So I mean, as per our discussions, it's logical to choose 2 power 0. That's 1. So choosing a gain of 1 is okay or not okay? Okay, buffer. So it's okay, right? I can have a buffer. So what's the problem? Right? I mean, the overall, I mean, till now we have been banking on the fact that the quantization noise is getting divided by some gain, right? If we have a gain of 1, we are doing nothing, right? So obviously, their gain cannot be any arbitrary number. So we have 2 conditions. One, it has to be power of 2. And that's simply for easing the, I mean, or simplifying our calculations in the digital portion, right? And the second portion is the gain has to be greater than 1, right? So what is the minimum gain? 2, right? 2 must be the minimum gain. But again, if I use a gain of 2, if there is a mismatch in this level, it's going to get overloaded, right? That's fine. So what people do is, instead of having a 2-level quantizer, that is a single bit ADC like this, let me copy it. You can do it, but again, you can't exactly correct it, right? There will always be some error that is remaining. You can't completely cancel any error. Okay. There'll always be some error. In principle, if you want to do any kind of cancellation, that's not going to work completely. There will be always some residual error. Okay. So the point is, now, if I have a gain of 2, having a 2-level quantizer is not going to work. Okay. So what people usually do is they have 3 levels like this. Okay, that is, they introduce one more quantizer, I mean, one more level in this characteristic. So this will again be half and minus half, and this will be 0. Okay, and you add this additional level so that this step characteristic is still a good approximation of this straight line. Okay, so let me draw the straight line also. Right, this is a straight line. So now, can you tell me from this what might be these voltages? Sorry, no, plus half is, remember. Okay, be careful, because we told that this value is half, right? If this value is half, this is half, isn't it? Right, this value is half. This is the input equal to output line, right? So this reaches a value of half at this point, right? So this is half, and similarly this is minus half. Is that clear? So now, can you guess what these voltages might be? Minus 1/4, fine. So that's what we do. We add an additional level at like this. Okay. So this again the 1/2 and minus half. This will be 1/4 and minus 1/4. So now how will the quantization error look like? So let me draw this straight line also. So how will the quantization error look like? Or most importantly, I'm interested in the maximum value of the quantization error, right? So how will it be? I mean, it's going to take maximum value only at the transitions, right? Only at the point of jumps, it takes the maximum value. So let's just look at this point, right? So if I have 1/4 here, it's going to jump. Let me draw this curve. What will be the height of this? One by 4, fine, right? Because at this point, the input is 1/4, output is going from 0 to half, right? So the error will jump from 1/4 minus half to 1/4 minus, sorry, 1/4 minus 0 to 1/4 minus half. Okay, so that's going to jump from 1/4 to minus 1/4. That's okay. Okay. This point is no. Hold on. Let me correct you there. We are not introducing this to correct for offset. The offset might still be there. Okay. And as we saw, if you want to accommodate for this offset in these transition points, we have to choose a lower gain, right? But the moment we choose a lower gain, it turns out it's going to be 1, right? That's not going to help us. Okay. So the point is, if you just have 2 levels like this, you can't choose a lower gain to accommodate for the offset. So that is why we are introducing one additional level here. Okay, with the expectation that this might be suitable for choosing a gain of 2. Correct. Yeah, it's not now effectively not a 1-bit ADC. Let me come to that. Now, I mean, since I have 3 levels now, this is no longer a 1-bit ADC, right? To represent 3 levels, you need at least 2 bits. Okay, let's come to that. So let's go to that later. But my question is, what is the maximum and minimum value of the quantization noise? Right? See, at this point, the curve is jumping, right? At this point, the input is 1/4. Okay. And the quantizer output is jumping from 0 to half, right? So the error will jump from the input is 1/4, and the quantizer output is jumping from 0 to half, right? So we take the difference 1/4 to 0. Okay. So which means it's going to jump from minus 1/4 to plus 1/4, right? So it will just look like this. Okay. Now that it is jumping from minus 1/4 to plus 1/4, if you use a gain of 2, what will happen? Is it fine or not fine? Now if you use a gain of 2, G times Q will lie between minus Vref by 2 to plus Vref by 2. Okay, so this is going to solve the problem. But as he correctly pointed out, now we have 3 levels. So this is no longer a 1-bit ADC. So what will be the effective resolution? Sorry, I have 3 levels, right? So, no, 2 can represent effectively four levels. So you just have 3 levels. What is the effective resolution? How can you find out? Sorry. Okay, if I have 8 levels, you say it corresponds to 3 bits, right? How do you say that? Log to the base 2, right? So we have 3 levels. Effectively, it's log to the base to 3. Okay, this roughly it's 1.5 bits. So this is usually called the 1.5 bit stage. Okay, or 1.5 bit ADC. But obviously, you need 2 bits to represent the output. But it has an effective information corresponding to only 1.5 bits. Okay, so let me explain one last thing before concluding. So let's say this is a 3-level quantizer. I have a gain of 2, one more 3 level, gain of 2. And let's say have, okay, this is 3 levels, okay. And this is a 4-bit ADC. So now can you quickly tell me what is the effective resolution? Sorry? 6 bits, okay. Is that fine? 6, right? So I have 4 bits plus 1 plus 1, that's all, okay. And similarly, you can have this 3-bit ADC, can put like 10 times or something, can get a higher resolution ADC also, right? You can cascade it multiple times, and finally you can have some 3-bit ADC or something and get a higher resolution also, okay? So yeah, let's stop at this point and we'll continue from next class.